Hi, and welcome to the third lecture for Math 232. We are going to talk today about length and angles of vectors in R2 and R3. Okay, so again, some vocabulary. We're going to have the length of the vector. That's our first item here, length of a vector. And the length of the vector, we also sometimes call it the norm of the vector or the magnitude of the vector. So those three words are interchangeable. And then we have an angle of a vector, and that is the angle between the x-axis and the vector measured counterclockwise. Product. The word product means to multiply. So that's the product of 2 and 3 is 6. That means to multiply two things together. And there is two types of vector multiplication. So we previously have seen how to add, subtract vectors and how to multiply a vector by a scalar. But as of yet, we haven't seen how to multiply two vectors together. And that process can be, there's two types. This is very different from regular numbers. So there are two types of vector products. There is the dot product and the cross product. We will be exclusively focusing on this guy here. Okay, and there's going to be a bunch more about this below. We will not be, for the most part, using the cross product at all. Part of the reason for that is that the cross product is only defined in R3. So it doesn't exist in R2, it doesn't exist in R4 or any of the other ones. So it's a sort of less general use, whereas the dot product is defined in all dimensions. Okay, then there's the word orthogonal. A nice word. I like the word orthogonal, and that means at right angles or perpendicular. So these, like that, those two lines are orthogonal. And a normal vector is a vector that is orthogonal to what is being referenced. So were we to have, for example, a plane, let's just draw a plane here. We can imagine this would be like, say, for example, the table, and then we have a ruler or something like that coming perpendicular down to the plane, then we would say that this line is normal to the plane. Or we can even in fact have it like that. We could have a curved surface and we could have a tangent line like that, and then we could have the line that's normal to the curve at that point, which means that it's perpendicular to the tangent line. Okay, so we use that word to mean something that is orthogonal to what you're referencing. Okay, so let's just see how to calculate these things. I think this lecture a little bit more straightforward than the last lecture on span and linear independence, which is, I think, a more conceptual and more difficult lecture. These things are geometric and I think much easier to see what's going on. Okay, so let's just make sure we can figure out how long a vector is. So we got to try to figure out its length, possibly called its norm or its magnitude. Okay, so and we're going to do this in R2. And so we have a vector, there it is, the vector v, and it has two components. Let's just call that v1 and v2. Those are just numbers, the x and y coordinate. This right here is a right angle. By the Pythagorean theorem, we could see that the length of this thing right here, the length of this vector is going to be the square root of v1 squared plus v2 squared. I'll try to be consistent there. v1 squared plus v2 squared. So we just use Pythagoras for that. And so here it is then, by definition, the length or magnitude or norm of a vector in R2. And we denote it this way with this double bar on either side, so that we would read that the norm of the vector v, that is the square root of v1 squared plus v2 squared. Okay, let's just do an example. We imagine a vector v, let's say v, the vector v, and let's have its components to being, say, 1 and 7. Okay, then we have that. In fact, let me just do it this way here. I'll do it this way. I'm going to change the order, actually, 7 and 1, like that. So we're going to have an x component of 7 and a y component of 1. And there our vector is going to be like that, looking like that. And then I would be able to compute the norm of that vector as the square root of the first component squared plus the second component squared. And that would be 49 plus 1, which is the square root of 50. And that is 5 root 2. Okay, so that is the length of that vector, this length right here, how long that thing is. Okay, some properties of length of a norm. So norms are always positive or zero. And if they are zero, then the vector is the zero vector. And also, if we multiply a vector by a scalar and then ask what the length of that is the same as taking the length of the vector and multiplying by the absolute value. Notice the absolute value signs, the absolute value of the scalar. Let's just see what that is. We've got a vector above there. Let's just take the norm of 5 times v, where v is going to be the same guy here. And that is going to be the norm of 5 times 7, 1. And that is going to be the square root. Let's see, 5 times, what did I pick such big numbers? 35 squared plus 5 squared, like that. And then I'm going to put that as the square root. I'm going to factor the 5 squared underneath here. 1 squared plus 7 squared. There it is. And that's going to be 5 times the square root of 50. And that is going to be 25 root 2. And you'll see that that is, in fact, 5 times the norm of v. So that's an example of b here. It's not a proof, not a proof. It's just to say we were taking this as to be true, and then I'm just demonstrating the truth of it with one example. So we can see that by multiplying by a scalar, you make the vector, the absolute value of that scalar longer. Okay, that's how you find the length of a vector. Then we have the angles between vectors in R2. So if we have two non-zero vectors, then we define the angle between them to be the smallest non-negative angle needed to rotate one vector to the other. So what does that look like? Like this. We have here v1, and then we have some other vector over here. Let's call it v2. And then the angle between them is this angle here, theta. So we imagine taking v1, rotating it on so it's on top of v2, and how how do we have to like what angle is that? So that is the way we determine the angle between. That's what we define to be the angle between them. And this right here is positively increasing angles. You have taken some other mathematics where you have seen the polar coordinate system. If you don't recall the polar coordinate system and how to exchange from the polar coordinate system to the rectangular coordinate system, now is the time to review that, because it's sort of you'll see an analogous things here, and also later in the course we're going to be talking about complex numbers where we're going to be going between polar and rectangular forms, and so that information needs to be regained if it has been lost in the interim. Okay, so here the angle theta rotates v1 onto v2. So we call that theta the angle between them. Okay, and then here we have a statement of a theorem, which we're going to show why it's true. And that is, if we have two non-zero vectors u and v, and theta and alpha is the angle between them, then we can compute the angle between them using this formula right here. The cosine of the angle between them is component 1 of vector 1 times component 1 of vector 2 plus component 2 of vector 1 times component 2 of vector 2. And then we divide that by the product of the norms. Okay, so in this case, we're thinking of the vector u as being u1, u2, and v as being the vector v1, v2, like that. Okay, the norm of u is the square root of u1 squared plus u2 squared, and the norm of v is the square root of v1 squared plus v2 squared. Okay, so we're gonna start this demonstration that this thing here is correct by recalling the law of the cosines. So have seen this probably somewhere before in an algebra course. If not, you feel free to look it up. And then of course, if you're not convinced of that, then what you would do is prove the law of the cosines to yourself before taking that as a fact before starting this proof. But we're going to take that as a fact, the law of the cosines. And so let's just draw a picture of what's going on here while we're doing this. And that is going to be, we have one vector here, v. We've got a second vector over here, u. And we've got an angle between them, alpha. And then this vector here is v minus u. Okay, so what we're doing here is we're going to apply the law of cosines to this diagram. That is telling us that where this thing here, let me just change colors. This thing here is being associated with C, and then this one's being B, and this is A, and that is B. Okay, so that's how we're thinking of this here. So we're saying C squared, that is the norm of V minus U squared, is equal to A squared, that is the norm of V squared, plus B squared, which is the norm of U squared, minus 2 times A, the norm of V, and U, the norm of, the norm of U, and then that's a multiplication, and then we're multiplying that by the cosine of alpha, the angle between them. Okay, so now we're just going to basically we've used this, and we've just written it out in our new language. And now what we're going to do is manipulate this around until we have the result that we desire there. So I'm just going to now write out, we know how to compute the norm of something. And so we're going to write that out in terms of the components of those vectors. So that's going to look like this. V1 minus U1 squared, the first component squared, plus the second component squared. And then on the other side, this norm here, that's going to be first component squared plus second component squared. Then here, first component squared plus second component squared. And then I'm just going to leave the rest of it. That's going to be 2 times the norm of V, norm of U, times cosine alpha. If you're following along with this and you think, oh yeah, I totally get what she's doing, maybe stop the video, finish the derivation yourself, and then start it going again and see that all is well. If it is, then perfect. That's better than just watching me do it, actually doing it yourself. Okay, here I'm going to expand these guys here. So I'll get V1 squared minus 2V1 U1 plus U1 squared. That's expanding that first term. Expand the second term. V2 squared minus 2V2 U2 plus U2 squared. And that is still equal on the other side to this thing up here. So that's, I'm going to recopy that, hopefully copying it accurately. V1 squared plus V2 squared plus U1 squared plus U2 squared minus 2 times the norm of V times the norm of U times cosine alpha. I'm kind of running out of space there. Cosine of alpha. Okay, now I can cancel a bunch of stuff out. Always a nice feeling. That can cancel with that. That can cancel with that. Where's the U squared can cancel with that. And I am left with the following terms: minus 2 V1 U1 minus 2 V2 U2 equals minus 2 norm of V, norm of V, norm of U, those are multiplied, times cosine of alpha. Now we're into algebra mode, and I'm going to just factor out that minus 2 and cancel from both sides. So I'm going to factor this out and then cancel that out like that. And I end up with V1 U1 plus V2 U2 is equal to the norm of V, norm of U, cosine of alpha. And we're getting really close. All we have to do now is rearrange and solve for the cos of alpha and put that onto the left-hand side there, and we get u1 v1 plus u2 v2 divided by the norm of u times the norm of v. Okay, there it is. So we're now convinced, I hope, that this is the way that we can calculate the angle between two vectors. Now I'm going to say what's going to come up here and going to be generalized, whereas this is hard to see how you would generalize this up into a higher dimension, so sort of more obviously, but what we have here is we're going to see that this thing here, right here, has a special, this is a special number. It's just a number, right? These are, each one of these things are numbers, and we're multiplying them together and adding it. So this is a special number. About to be seen how we're going to do that. First, before we identify what that is, we are going to have an example here, finding the angle between two vectors there. Let's just draw them out. Where are we at here? 1, 2. So we're here at 1, 1, 2. There's a vector right there. And we're at -1, 5. So we're here -1, and then we're 1, 2, 3, 4, 5. So we're here at 5, and we got our second vector here. Okay, so what we're going to do is try to find the angle right here, alpha. The angle between those. So, I mean, we're just simply going to apply this here. Cosine of alpha is what? U1, I have it written here. I won't write it out again. U1, V1. Let's write that. U1. Well, let me just write here. So U is equal to this here, 1, 2. And V is equal to this guy here, -1, oops, -1 and 5. Okay, so I can see what the U1 is 1 and U2 is 2, V1 is -1 and V2 is 5. So I'm going to put that in, U1 multiplied by V1 plus U2 multiplied by V2 divided by the norm of U, and that's going to be the square root of 1 squared plus 2 squared, multiplied by the norm of V, which that's this norm of V, and that's going to be -1 squared plus 5 squared. There. Okay, so I have now an expression for the cosine. Let me just compute what number that actually is. That's the cosine is going to be 9 divided by √5 times √26. So that means that that alpha is going to be the inverse cosine of 9 over √5 √26. Okay. Now, clearly, if you were asked to do something like this in a quiz or a midterm or something like that, you would simply leave the results like this. We won't be using calculators, and so you just leave the results like that in the calculator ready form. And I'm going to just do that as well. Okay, so we do have an expression for the angle. You can use your calculator to see exactly what that is. My strong preference is, of course, we deal for the most part angles in radians. Okay, so we saw, let me just, we saw this thing highlighted up here, the thing that's in the numerator there. That thing has a special name. That is called the dot product. So let's get a definition of what that thing is. And this is an extremely important thing, in that it's a tool that we're going to use many times in many different contexts. It is the way that we multiply two vectors together. Okay, so having only seen addition basically and scalar multiplication so far, now we're asking, what does it mean to multiply two vectors together, and what does it look like? Okay, this is not as straightforward a question as it would be, for example, for numbers. Okay, so the dot product, which has another name too, is sometimes called the Euclidean inner product. Okay, so we've got two vectors, u and v, and we're going to multiply them together, and this is our definition of multiplication. And we read this like this: u dot v, and what we do is we multiply the first two components together, and then we add the product of the second two components. That's how we calculate the dot product. We can take a dot product of a vector with itself. That looks like this. First component times first component plus second component times second component. Okay, that is the dot product of u with itself. That looks like this, u1 squared plus u2 squared. And you will notice that that is the norm of u squared. So the dot product, let's just write that again, the dot product of a vector with itself is the square of the norm. Okay, obviously we could take the square root on both sides and say that the norm is the square root of the dot product. Okay, why don't we just do one quick example of taking the dot product of two vectors. Let's take u equals to 1, 1, 4, and v is equal to -1, 3, like that, and then say, what is u dot v? So u dot v, we take the first component of u multiplied by the first component of v, and to that we add the first component of, the second component of u multiplied by the second component of v. And that is -1 plus 12, and that is 11. So the dot product, when u and v are these two vectors, the dot product is 11. Okay, notice something important. We are multiplying together two vectors and we're ending up with a scalar. This always happens. So the product of two vectors, the dot product of two vectors is a scalar. Okay. All right, so I'm going to make a calculation here. To determine what this is here, okay? Let's just draw a picture of what this looks like. I'm going to just draw two vectors over here, u and v, and just show you. I'm going to first try to give the geometry so we can see why it's called the parallelogram equality. So there is u, there is u, and there is v. Okay, so u plus v is, we put u there, and I'll maybe just change colors here. So this vector right here, that guy right there, I've moved v over. This guy, the blue guy right there, that is u plus v right there. And then this vector here, this guy here, right here, and I'm just going to sort of complete this line right here too, so you can see the parallelogram on the outside there. This vector here is u minus v. That guy right there is u minus v. Okay, so let's see what if I take the norm of u plus v, so that is the length of u plus v squared plus the length of u minus v squared. Now we can see where those lines are. What is that equal to? So I'm going to go ahead basically and expand this out algebraically. I'm going to probably skip some of the steps just because it's basically algebra at some point. I'm going to start by, I'm going to start here. What I'm going to do is I'm going to write out the expression for that. That's going to be u1 plus v1 squared plus u2 plus v2 squared. And then we have the second term here that is going to be u1 minus v1 squared plus u2 minus v2 squared. So that is what this thing is equal to on the left. I don't know what the right hand side is. I'm trying to find an expression there. So I do the same thing I did before. I expand out these terms and attempt to put them together in a way that I can do something with. And then so that here is u1 squared plus 2u1 v1 plus v1 squared plus u2 squared plus 2u2 v2 plus v2 squared plus, I'm going to maybe even go down below, u1 squared minus 2u1 v1 plus v1 squared plus u2 squared plus 2u2 v2. Nope. minus, a little too fast here, minus 2 u2 v2 plus v2 squared. Okay, so that I have that expanded out now equal to this, both of those lines together. And then I, as you can see, I can do some cancellations. And I end up here with 2u1 squared plus 2v1 squared plus 2u2 squared plus 2v2 squared. And what is that equal to? That is 2 times the norm of v squared plus 2 times the norm of, 2 times the norm of u squared plus 2 times the norm of v squared. And that is what where I wanted to get to actually. So I've got that, I'm going to erase this here. I've got that this guy right here, that guy right there, I've managed to go through algebraically and show that this is 2 times the norm of u squared plus 2 times the norm of v squared. So just look at this thing then. We're looking at the lengths. What we're saying is that the length, maybe what colors have I used? Let's just take a look at what it says. On the left-hand side, it's telling you the length of this guy squared, that guy squared, plus the length of that guy squared is equal to 2 times the length of this guy squared and this guy squared. Okay, that's the parallelogram equality. You can take a look in Wikipedia, just go, parallelogram equality Wikipedia, and you'll see it there. And this is one way of showing it. Okay, so let us just take a look at some of the algebraic properties of the dot product. Okay, they are here. The dot product commutes. U times V is the same as V times U. We have distribution. Okay, so we have left and right distribution. We have the ability to distribute the scalar throughout. If we take the dot product with the zero vector, we get 0. And then we have here distribution over subtraction. So let's just take a look at proving this one here. We're going to prove 2a using the definition of the dot product. So here, what we do is we simply write out what the both of them are and try to show that they're equal. So let's write out what u dot v is. That's equal to u1 v1 plus u2 v2. That's the definition of the dot product. Let us write out what v dot u is. That is v1 u1 plus v2 u2, also by the definition of the dot product. Okay, now this one here, I'm going to rearrange around. I'm going to say, hey, but that's actually u1 v1 plus u2 v2. Why? Commutativity of scalar multiplication. Okay, what does that mean? Scalar multiplication is multiplying numbers. Scalars are numbers. So that is this. I already know this is true. Okay, so because these are just numbers, this is a number, a product of 2 numbers, I can switch it around. So I'm saying why I'm allowed to do that. And then I notice, hey, that is u dot v. Okay, so now I have shown that v dot u is the same as u dot v. So the dot product is commutative. Okay, now here is a key feature of the dot product. If you take the dot product of 2 vectors and you get 0, dot product is 0, then the 2 vectors are orthogonal. So this is a very quick check to understand whether 2 vectors are at 90 degrees to one another. Okay, let's take an example. 2 examples, in fact. This is really important. I mean, we're often going to be wondering, are these 2 things orthogonal? Simple check, dot product. Is the dot product 0? Yes or no? And so this is an important feature. Okay, so let's just draw a couple of pictures. And we're here like this. Here's our axes. And let's just take the standard basis vectors for R2. So there is 1, 0 and 0, 1. And let's take the dot product. 1, 0 dot 0, 1. And then I would take 1 times 0 plus 0 times 1, and it's equal to 0. And those two, and these two things are at right angles. Okay, let's take another pair of vectors and ask the same question. Let's take the vector 2, 3, 2, 1, 2, 3. There it is, 1, 2, 3. There it is, 2, 3. And then let's take the vector. Okay, so we're going to take the vector here, 2, 3. And we're going to take the dot product with another vector. Let's take the vector 1, 2, minus 3, 2. So that'd be this vector here. Okay. Now it does look like they're at right angles, but you know, my drawing, you can't look at the drawing and tell. So what we're wondering is, you know, is this angle in here, is this angle a right angle? So what we do is we take the dot product. The dot product here is 2 times minus 3 plus 3 times 2, and that is equal to 0. Tick. These things are for sure a right angle. Okay, so that is what we can learn from taking the dot product of two vectors. It's one thing that we can learn. That the angle between them is a right angle if the dot product is 0. All right, so the same thing happens in R3. This is just a scaling up by one dimension. And of course, we're going to see a little bit later that we just simply can expand this to R4, R5, R6. But let's just do a couple of examples in R3 where we can still visualize things. Apparently, some people can visualize things in their head in R4. I cannot do this. I always have to scale back to an example in R2 or R3, sort of see what's going on, and then sort of trust that it's working. Well, you can prove it, but I can't get the same visual picture in R4 or R5. Okay, so here we are in, we're going to be in R3. So let's just take two vectors. There's a vector u looking like this, 1, 4, minus 2. And a vector v looking like this, minus 1, 2, 3. Okay, we've got two vectors that are in R3, 3 components. Let's take the dot product. That's going to be like this. The first component times the first component plus the second component times the second component plus the third component times the third component. And if I made an arithmetic mistake, that's like minus 1 plus 8 minus 6. Let's see, that's 1. The dot product is 1. No, it's a scalar. I'm going to emphasize this for the first little bit. The dot product of two vectors is not a vector, it is a scalar. Okay, so I can now write here u dot v is equal to 1. We know that these two vectors, we're not drawing them. In fact, it's hard to draw these on a piece of paper. We're not drawing them, but we actually now know that the angle between these two vectors in 3 dimensions is not a right angle. Okay, they're not orthogonal. All right, so we had seen before a formula for computing the length of a vector, and we can now express that in terms of the dot product. I think this is fairly, I mean, you look at this, you can see it's the dot product of u with itself. So let's just do an example here. Let's take the vector u, I don't know, let's take the same one from above like that. And then we can take the norm of u, and that is the square root of 1 squared plus 4 squared plus minus 2 squared. We've done this before. That is the length of u, and that works out to be minus the square root of 21. Now let's take the dot product, u dot u, and that is equal to 1 times 1 plus 4 times 4 plus minus 2 times minus 2, and that's equal to 21. And then you can see that the square root of u dot u is equal to the square root of 21. So it is the case that the norm, we saw this before too, the norm of u is the square root of the dot product. So it's kind of handy sometimes if you want to know how long is that vector, you simply take the dot product of it with itself and then take the square root. All right. How about if we want to know what the distance between 2 points is in R3? So we've got 2 lines in R3, and we want to know what's the distance between the tips of those 2 vectors. and we denote that by the distance between u and v, and that is the norm of v minus u. Okay, so the norm of v minus u, this is here the norm of v minus u, and that is equal to the square root of v minus u dot v minus u. There it is. Okay, so then we just established above the norm of a vector, which is considering the vector now to be v minus u, is the square root of the dot product of that vector with itself. Okay, which then is this guy here, the square root of v1 minus u1 squared plus v2 minus u2 squared. This is the dot product, and v3 minus u3 squared. There it is. Okay, some properties of the dot product. I'm sorry, of the distance between two vectors. So distance is always positive or 0. You can sort of see if you have, there's no way of having a negative distance. The distance between my house and SFU is either I live right at SFU, at which point it's 0, otherwise it's some positive amount. It doesn't matter in which direction I drive, it's still a positive distance. Okay, distance is only 0 if the two vectors are equal, and the distance between u and v is the same as the distance between v and u. That follows from the commutativity of the dot product. Okay, let's take an example. Let's take u here equals 1, 5, and v is equal to minus 1, 4. Okay, so we'll draw a picture of this. Okay, actually, it occurs to me I'm going to go draw a picture, and then I'm going to calculate the distance between u and v. If you're completely following along and you think to yourself, oh, I can probably do this, stop the video, do it on a piece of paper, and then restart the video and say, okay, I did it right, perfect. I didn't do it right. Oh, what did I miss? And then you'll learn something right then, and that'll be a good moment, right? You want to be actively doing as much as possible yourself. Okay, so here's my two vectors. I'm going to draw them, and so I got 1 and 4. My first vector right there, and oh, I got 1 and 5. Sorry, let's get here. I can fix that by changing that to a 5. 1 and 5, and then I've got minus 1 and 4. That's that guy right there. Okay, and then I'm going to ask what is the distance between them, and that is right here. That vector right there, which is v minus u. Okay. Okay, let's figure that out. V minus u is equal to v is minus 1, 4 minus u, which is 1, 5, and that is minus 2 minus 1. There it is. Okay, so I can now take the dot product, v minus u dot v minus u, and that is minus 2 times minus 2 plus minus 1 times minus 1, and that is 5. So the norm, the length of v minus u is equal to the square root of that dot product I just calculated, v minus u dot v minus u. There it is. And that is equal to 5 from above. So that is the square root of 5. So, and that is the distance between u and v. There we go. Okay, so that is a way, we have a way using the dot product in order to calculate the distance between two vectors. All right, next thing, we're going to talk a little bit more about the scalar equations of lines and planes, and we're going to incorporate the dot product, particularly in R3. Okay, so let's just remind ourselves of this. We have seen the vector and parametric description of both lines and planes. Okay, so let's just remind ourselves of that. We've got lines as vectors with the vector description. So I could have, for example, a line, and let's just call it L1. It would look like this. All vectors T V1 such that T is in R. And that is a line through the origin. Okay, there's no point there. So this is through the origin. Okay, you can see that when T is 0, the zero vector is in the set. Okay, and here's another example, L2. That is, I'm going to say that vector looks like this, V1 plus T V2, such that T is in R, a real number. So this is not through the origin. That is, of course, if V1 is not 0. I mean, if V1 is 0, then it basically reduces back to the previous case. But if V1 is not 0, then that is a line not through the origin. Okay, and then we saw, for example, L1, we could represent it parametrically in the following way. So I'm going to take this vector equation here and represent it parametrically. That is, x is equal to T V1 and y is equal to T V2. And then I will take this line, L2, and represent it parametrically. That looks like this. X is equal to V1 plus 2T. Oh, that's confusing because that's the whole thing. So let's call that V11 plus TV21. And then Y is equal to V12, the second component of the first vector, plus the second component of the second vector. Looks like that. Okay, so we have the lines represented vector equation and parametrically. We have also seen plane. In R3, we've seen the plane, and we saw that as a plane looks like this. V1 plus 2, sorry, T V2 plus S V3 such that S and T are in R. And remember, we need the linear independence of V2 and V3. Be careful, you can get bitten by this one really easily by looking and going, oh, look, it's a plane. There's 2 degrees of freedom, and then not realizing that V3 depends on V2. Okay, so really caution there. I'm gonna, it's easy to make that mistake. So that is, and V2 is not equal to some scalar multiple of V3. Okay, and then of course we can write that out parametrically as well. Why don't you do that as an exercise? Write out the parametric version of that for the plane. Okay, we also know how to represent a line with a scalar equation. We know that we can write y equals ax like that. If it's a line through the origin, we can write y equals ax plus b if it is a line not through the origin, given that b is not 0. We also have the standard equation of the line, ax plus by plus c is equal to 0. And this form is easy for checking if a point is on the line, right? Any one of these forms here. So if I give you a point is whatever, doesn't matter, 2, 5, the point, 2, 5 on the line, you can easily substitute it in to one of these equations and go yes or no, right? It either satisfies the equation or it doesn't. So that's this form of the line is particularly nice for checking if a point is on the line. Okay, now we're going to define a normal to a plane. So what does it mean? Define a normal vector to a plane. That is the vector that is orthogonal to any line segment in the plane. So we have a plane. This is now, I'm going to be sort of considering this my tabletop, if you will, like that. It's hard to draw on 2 dimensions in, you know, a 3-dimensional thing in 2 dimensions, but I am imagining a flat plane, and then I am going to draw a line that is, sorry, and then I imagine any line segment in this plane. There's a line segment in the plane, and then I'm going to draw a vector that is orthogonal to that line. So that line could be any line here in the plane, right? That that thing sticking out is orthogonal to all of the lines in the plane. Okay, sticking out of the page. Okay, so notice something here, and that would be if we take any 2 points in the plane. So let's just write this out so we can see what's happening. Take any 2 points in the plane. Okay, let's call them P1 and P2. Like, for example, P1 could be here and P2 could be here. P1 and P2. So we got 2 points in the plane. Then we're going to draw a vector between them. Draw a vector between them. That is I'm going to call that vector V, and that is going to be P1 minus P2. Okay, you're simply just drawing a vector between, we think of those 2 points, we actually just think of them as the terminal point of some vector, and then we draw the vector joining them. Okay, so that I've now managed to draw P2 minus P1 here. Okay, right there. Okay, then, and then let's call this guy sticking up here. Let's call this vector N. We often use this notation when we call a vector N. It's often because it is a normal. We're like in this problem, this vector is normal to something. So it doesn't have to be that way. Of course, we could call it something else, but it is a convention to call the normal vector N. So this isn't. We have here. We've drawn this vector V in the plane here, and we let me get that there. V. The vector V is there in the plane, and then N is at right angles to it. So we're gonna call it N. So our mind's like, hey, that is a normal vector. Because it's a normal vector, it's at right angles. We have the important property that N dot V equals 0. Right? The dot product of N with that vector V in the plane is 0, because the dot product is 0 when 2 vectors are orthogonal. Okay, we're going to use this to figure out what the scalar equation of the plane is. Okay, so here's the process. We're going to think of P, some point P. P1, it's got 3 components. We're in R3. 3 components, being a fixed point in the plane. Okay, we fix some point in the plane. Then we let X be with components X1, X2, X3 be any other point in the plane. So X can, move around. We've got 1 point fixed, and then we're like, hey, take any other point in the plane and could call that X. So X can change, and P is fixed. Okay, then we know that the normal vector dot X minus P, that's the vector between our point X and our point P, is 0. They are orthogonal. That means that the vector, maybe I'll even write it this way to try to be this vector, N1, N2, N3, that is N, the vector N, dot the vector X1 minus P1, X2 minus P2, and X3 minus P3, that dot product is 0. Okay, let us write that dot product out. The dot product is a scalar. So we're going to write this out. It's going to be N1 times X1 minus P1 plus N2 times X2 minus P2 plus N3 times X3 minus P3 is equal to 0. Okay, now I've got an equation actually just with numbers and my varying point X, which has 3 components, X1, X2, and X3. So now I'm into number land. I do not have any vectors anymore. Okay, so now I'm just going to be rearranging the terms. I'm going to distribute out and rearrange the terms. And what do I get? N1, X1 plus N2, X2 plus N3, X3 is equal to N1, P1 plus N2, P2 plus N3, P3. What does this look like? This is highly exciting, folks. What does this look like? This looks like this. AX plus, maybe I don't want to use a capital. AX plus BY plus CZ is equal to D, where ABC is the normal vector. Okay, in this case, D is this product right here. So product and sum. So here, what we've got is this thing here is this is the standard or the scalar equation of the plane. Okay, we previously saw the vector equation of a plane, the parametric description of the plane, and now we see how to, using the idea of that normal vector to get the standard equation of the plane. Further, we can see that the normal vector basically is sitting right there in the standard equation. Okay, that is it. That is our excitement for today. And there's a bunch of exercises for you to do. I highly encourage you to do these. Why did it not scroll up? Okay, hang on, I've scrolled up on my thing here. Oh, I seem to have a lag between the computer that's recording this and my Surface Pro, which I am writing on, and it didn't scroll up. But anyways, it's luckily we're near the end here. And the next page down, as you can see on your notes, is a bunch of exercises to do. Please do those, and we will be back. We'll begin our Zoom session to answer questions about these, and we'll be back with the next lecture shortly. Thanks a lot, guys. Bye.